So we are going to jump in and get started. This is the calendar. So on the intro page of the OneNote is not correct. So anyway, here is your homework for today for the 4th of March. And then it just kind of goes through. So we're just in chapter 6. So we are really going to be done with this little section. We back up. This unit has 3 sections. We're going to be done with the first one on Friday, okay? And then we'll move on to section number 2, and then those kind of go together as kind of A and B sections, but it's all good. So anyway, there you go. Yes. Oops, you can't see it. Let me show you. Please wash your hands. Oh my gosh, you guys, I know your moms and dads have been telling you a lot, but I'm going to keep telling you, wash your hands. We don't have time to get sick. All right, we're going to do something. We're going to do one more problem. We're going to do a demo, a bunch of problems. It's going to be great. A reminder that this week we're going to problem solve today and tomorrow, and we're going to do our lab analysis from this lab on Friday. So I will give you your data back, and it will be a beautiful thing. Okay, we're going to do some linearization, some lab analysis. So just know that that's coming. It'll be fun. Okay. So I'm going to show you this warm-up problem, and it's not just a picture. In fact, it's a thing. It's right here. So I honestly, true story and true confession, I borrowed this from Miss McGrain for my regular physics class. We already did this unit in regular physics. And then I just never gave it back. And I was like, oh, we have it, and we're going to use it before I go return it to her. So sorry, Miss McGrain, I'll give it back to you soon. So here's the situation. She got this from, I don't know, some store, and then it has this other thing that goes with it, but she just sawed it off, like literally. So we just had the little rampy thing, okay? So I'm going to start the ball at the top, and it's going to roll, roll, roll. The question that I'm posing to you is, when it gets to here, where is it going to go? Is it going to go this way? Is it going to go this way? Like, I want you to draw a little picture. So I want you to draw from the top, little warm-up question, where is it going to go? It's going to keep spinning around, go back up? I don't know. Physics can do a lot of things. You want to look at it? Here you go. That would be amazing. Amazing. Right. So our 1 minute has passed. I want to know what you said. What kind of information did you add? So maybe we'll start over with this table. Is that okay? Tell us something that you put down there, and then we're just going to kind of collectively write things down, because I think that a lot of you have got it, but I just want to make sure that you've got all the pieces. So can I volunteer somebody from tables? What is that, 13 or 14? What'd you guys say? Okay, so when the ball reached the bottom, it traveled, what'd you say? Along the tangent line. You said something else, but I couldn't quite hear it. That it wanted to follow. Yeah, so if we look at it from above, this was like the end, and it was going around, and it was going around. So here's that ball, and it's going around and around. But at this point here, it just went that way, right? Right towards Sid. Okay. Should I draw you in the picture too, so we don't forget next time? Okay. What color do you want? My blonde. Okay, so like orange probably, right? That's kind of what I got. So there's Sid from above, and the ball is going to go straight towards Sid, right? Cool. All right. What else did you say? Brady, what else did you have written down about that? Pass. Okay. Drew, what else did you say? Okay. So let's talk about, can I back you up for just a second? Once it leaves the ramp, this thing, it doesn't exist. So when it's on the ramp, when it's going down the ramp, can we do that part? Is that okay? So as the ball is rolling down the ramp, what is going on? So the centripetal force keeps the ball on the ramp. And then what did you just say? Because you said one more thing that is exactly what I wanted you to say. It's pretty much just the wall. So here's the thing, and this is the really important piece that I want to make sure that you know. So this was the wall. A force has to be an interaction between how many objects? Two. Is centripetal an object? No, it's an idea, right? It's not an object. So you should never, ever, 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 ever write centripetal force on a free body diagram. In fact, I would urge you never to use the phrase centripetal force. I'm not going to kick you out of the room for doing it. I'm not going to scream at you for doing it, okay? Because it is accurate. But the reason I would urge you never ever to use it is because it gets confusing and then people are very, very tempted to write this on a free body diagram. Okay? So I love the fact that as Drew was talking about, he was like, it's this thing, and oh yeah, this it's really just the wall. So really what we're talking about, and this is the key here, is that in, here, I'm just gonna highlight, like right here, when the ball is going around and around, the thing that's keeping it from moving out this way, right, moving out along the tangent, is that the wall is pushing on it, right? So the net force in the x direction, it's about y stuff going on, and I don't want to break the gravity, like we're not going to do that right now. But anyway, in that kind of, in this plane that we're talking about, the thing that's pushing on it is the wall. It's the force of the wall, or we could even call that a what kind of force? The wall applies what kind of force? It might be applied, but there's another like more specific one that might be even better. I heard it maybe. Yeah. So the normal force, or the force of the wall on the ball, I feel like I'm doing a little Dr. Seuss thing there. The normal force is what causes a centripetal acceleration. Okay. Doing these problems, solving this kind of problem, or looking at these kind of situations, the thing that you have to remember is that a force is always an interaction between two objects, and you have to be able to identify which force or which object is pulling or pushing on the object that's moving in a circle, okay? And whenever you have this circular motion business, what the result is this thing called centripetal acceleration. We said, I think, right at the very end what the word centripetal means yesterday. Do you remember what centripetal means? Center seeking. Yeah, center seeking. S-E-E, that's right. Seeking. Okay, I appreciate you. I was like a level 3 speller. I try. Okay. All right. I'm going to make you guys get out of your chairs again. Come sit on the floor. We're going to do like, it's not really story time with Miss Carbling, but okay. So on your paper, you're going to go ahead and draw this picture just with me so that we can remember the excitement of the yo-yo demo. Are you ready? So we're going to go ahead and draw ourselves a little circle. Am I frozen? I am. I am. There you go. All right. So I'm going to draw myself a little circle. That was not a perfect circle, but you get the idea. Like that-ish. I don't know if this is going to erase the whole thing. It will. Rats. Oh my gosh. Hold on. You draw your circle. I'll draw my circle. Perfect. Okay. That's what you say? Well, it's close enough. You make your circle perfect, and I'll make my circle pretty great. Oh. So there's the yo-yo at a couple different places. And then I'm going to go ahead and draw my string to the center at a couple different places. I'm going to decide for my picture that my yo-yo is going in this direction around the circle. And then we're just going to write down a couple things just so we kind of keep in mind what's going on here. Okay? So if, and Sid, I apologize that I didn't get to do this when we were down here. I apologize. If you were standing right here and this was going around like this and I let go right here, where's that yo-yo going to go? Probably towards you, right? But wait, hold on. If I let go here, is it still going to go towards you? You were just trying to be agreeable, weren't you? But you got to be careful about what you're agreeing to. Yeah. Why? Because the tangential velocity, well, it's supposed to be exactly a tangent, and that's really not. Eden's going to tell me it's not exactly 90 degrees, so I'll try a little better. Is that better, Eden? Okay, thanks. Okay, well, you do it better on yours, and I'll do better next time. Okay? The tangential velocity is always, maybe, it's always going to be the same magnitude, okay? Same magnitude because it's not speeding up or slowing down. But it's going to be in a different direction, isn't it? And that different direction means that it is indeed accelerating. Okay, because it's changing direction. So again, we can figure out where that acceleration is going, which way it's pointing. And what did we decide about the direction of that acceleration? We just talked about this when we were sitting up here. Which way is it pointing? That acceleration is always pointing toward the center. Okay? It is center seeking. It is a centripetal acceleration. I kind of mentioned this yesterday, but I didn't really explicitly say it, so I want to write it down really quick right now. All of the stuff that we're talking about today and in the next couple of days go into this thing called uniform circular motion. I just wanted to make sure that you were comfortable with and you understand where this is coming from. Uniform just means that it's not speeding up or slowing down. So it's the same speed, moving in a circle, and it's motion, right? But the uniform is that it's not speeding up or slowing down. So that means that it's only accelerating tangentially, right? Or in the linear motion, it's not like omega is not increasing or decreasing. You with me there? If we go back to our rotational stuff, omega is not getting bigger or smaller. It's just that we've got an acceleration towards the center of its motion. Okay, I just want to make sure that I'm catching everything here. Oh, yeah. So then we need to actually define what this acceleration is. What do you think? Oh, hold on. I have to do one more thing. I'm sorry. I keep kind of bouncing around. I want to do one more picture of my yo-yo, but I'm going to do it from the side. Oh, hello. Again. There's the floor. There's my yo-yo. You told me this before, but what forces are acting on my yo-yo? Gravity, the force of the earth. Fg. What else you got? Tension? This is the, oh my gosh, what is going on? Undo. I don't even know. Force of the string on the yo-yo. Ft. What else you got? Normal force, which is the force of the floor on the yo-yo. And which of those forces is causing the acceleration? Just the tension, right? Fn and Fg are equal in magnitude, opposite in direction. A Newton's third law pair? No, Ira says, why did you say that with such gusto? Why do you feel so strongly about it? Right. So if I had the force of the floor on the yo-yo, what would be the third law pair that goes with that? Indeed. Yeah. Does that make sense? Just trying to remind you and hit that home so that it makes sense. Okay. Fantastic. Now, oh yeah. So and then this is that's a pulling in towards the center force. And yes, we need to define how big that centripetal acceleration is. What do you think might impact the size of the acceleration, the centripetal acceleration, as I'm spinning this thing around? What do you think might impact it? I'm going to let you do this little brainstorm at your table. So my question is, what might increase or decrease the acceleration? I'm going to let you talk at your table for 30 seconds. Go. Come up with a little list if you can. Just carbling? Oh my God. All right, my friends. So tell me, what physical characteristics might impact the centripetal acceleration of this object? Autumn's got one. She's got it in her head. She doesn't want to forget. What you got, friend? Whoa, hello. I don't know what just happened here. There we go. The mass of the object. As the mass goes up, what do you think is going to happen to the acceleration? Okay. So as m increases and everything else stays the same, acceleration is going to go down. That's what our gut feeling says. All right. I'm going to call on you again, Brady. What you got? The radius. The radius of the circle, as that goes up, what do you think is going to happen to the acceleration? Goes down? He says that with a question mark. Should I put a question mark here? Oh, okay. You sounded, okay. Do you feel confident? I mean, like, I feel like people around you are feeling confident. Okay. I know. I put the question mark there. I just want to make sure. All right. Let's see. TJ, what else you got? The density of the string. Now, I appreciate that. So what would the density of the string impact? The mass of the string. How is the mass of the string going to impact the acceleration of the yo-yo? Well, that's what I'm kind of thinking. Eden's trying to bail you out. Okay. What? No. It's okay. We're all a family and we're all learning together. So what did you say? Oh, so she said, did you hear what she said? Oh, because I keep talking over you. Oh my gosh. I know. Jeez. Say it one more time. It could change the tension, right? So yeah. So we could say that. Or the net force that's causing our thing. So F net, or the tension force, if the net force gets bigger, oops, I need to put an up arrow, gets bigger, what's going to happen to the acceleration? It's going to go up. A is going to go up. All right. Now, anyone else, did you guys come up with more, or did they get all yours? Yeah? Chris, would you like to add one? The velocity? And if VT goes up, what's going to happen to the acceleration? It's going to go up. How do we feel about all this, friends? Okay. So we need to put all this together to see if we can come up with some relationship stuff. So I heard you when we were talking about the F stuff, you're just reciting some Newton's second law stuff, right? That A equals what over what? Or F equals MA, right? So A equals F over M. So we're going to say that the centripetal acceleration, oops, I was going to write that in green, but it doesn't like to write in green today. Let me try again. Here we go. Centripetal acceleration, like any other kind of acceleration, nothing changes, right? A equals F net over M. As M goes up, A goes down. As F goes up, A goes up. That's all well and good. This is true. This is just the same stuff we've always known. Okay? But then we're also going to throw in another relationship. A relationship between radius and velocity and acceleration. You tell me that as radius goes up, acceleration goes down. So where would that live in the relationship for A? Denominator, right? Because just like M, as M goes up, A goes down. We said that up here. Same thing for the radius. So we're going to put that down in the denominator. Okay. As the radius of the circle goes up, if everything else stays the same, the acceleration is going to go down. And then the other one here was velocity. We said as the velocity goes up, the acceleration goes up. So that means that the velocity needs to live in the numerator. Now there's a little bit of extra physics that lives in there because it's actually velocity squared. Okay. So A sub c, and I think that this exists on your equation sheet, but you can double check for me. I see that a couple of you have it out. Can you double check that for me? I think it lives on there somewhere. Where is it? I believe you.
It's like the
oh, I was like looking at the very top of each box. Yes, the sixth equation down. It is there. A sub c equals v squared over r. Bam. There it is. Okay. All of the rest of the physics is the same. It's all the same. We're going to try a problem out real quick. We got a few minutes. This one's super simple. I've got one super simple one, and I got a couple more that are a little more exciting. Here you go. A 150-gram ball on the end of a string is revolving uniformly in a horizontal circle of radius 0.6 meters. The ball makes 2 revolutions per second. The question is, what is the centripetal acceleration? I'm going to strongly encourage you, because we haven't done problems like this for a while, to jump yourself back to the guess method, right? Jump yourself back to givens, unknowns, equation, etc. I'm going to let you work for a couple minutes and then we'll discuss. Does that sound okay? You got this. All right. Let us do this. Did you get an answer? Let me back up. Let me start there. Chris said you had an answer. Would you like to share your answer with the group? About. I mean, that's a lot of sig figs for an about answer, but okay. Centripetal acceleration, you got, what'd you say? 7.5 meters per second squared. How do we feel about that, friends? Anybody need me to go over this? Okay, let's keep cruising then. If you need help, because I'm going to give you another problem. If you need help, let me know and I'll come over and help you. So here's the situation. Do you guys know the Addams family? Yeah. And things like the hand, I imagine that this is just the hand swinging a ball around. Yeah, yeah. If you know the Addams family, go watch the Addams family. It's good family classic. Calculate the force a person or thing, not thing. Is it thing or thing, right? Because it is the one with the hair. Calculate the force a person must exert on a string attached to a 150 kilogram ball that makes the ball revolve in a horizontal circle with a radius of 0.6 meters. Oh, it's like you've seen these numbers before. The ball makes 2 revolutions per second. Okay? So it's just another step in the same process. I want to know what the tension force is. Okay? What is the tension? So, did you come up with an answer? Yes. What kind of answer did you come up with? 14.205. We'll just go 14.2. What are the units we're doing? What are we trying to find? Force. Okay. Now, question for you. Where would I draw this force? This is the force. This is the force that's causing what kind of acceleration? Centripetal acceleration, right? So this is A sub c. So I heard some, oh my gosh, this is so simple. It is so simple, except there's one little piece here. There's one little piece I just want to talk about. You remember on Thursday of last week when we were whirling those stoppers above our heads, right? And I told you to get as close as you can to a flat, to a horizontal circle, right? Is it possible? Is it possible to whirl something above your head and make the circle make the string exactly flat? Lucy's shaking her head no. Why do you think no? So it would be hard. I agree. So let's not worry about the little tube and all that crazy stuff. If I try and whirl this, I'm not even wearing goggles, so whatever. Is it possible for it to get exactly flat? I see some yes, I see some no, I see some. Turned over here going with this, Miss K. They drew a free body diagram for you, didn't they? How many forces are acting on this object? two. One of them is one we know well, right? It's the force of gravity. Is the rock or the yo-yo or the stopper, is it moving in the up or down direction at all? It's not accelerating up or down, which means that there has to be a little bit of tension pulling which way? Up. Are you with me here? There has to be a little bit of the tension that pulls up this way. So Ft in the y direction that is counteracting mg. The force that you just calculated was Ft in the x direction. You with me there? So if you were going to be really, really careful with this, you would have to figure out what that angle was. And you'd have to calculate Fty, Fty, Ftx, and then you can find the result. I'm not going to worry about it for today. But have a great day. Yeah, for sure.